While we're not able to take questions now, please take the opportunity to ask questions on the hub. The authors may be able to answer them there. For our next talk, we'll keep in the same domain. We're continuing with fashion, with semi-supervised visual representation learning for fashion compatibility from Ambareesh, Revanur. Please go ahead.
Yeah, am I audible?
Yep.
Yes. Yeah, I guess so. Hi, my name is Ambareesh. I am a graduate student at Carnegie Mellon University. I am presenting this work on semi-supervised visual representation learning for fashion compatibility. This work was done during my internship with Walmart Labs in India. In fashion compatibility, we are interested in recommendation of fashion items that go well together. For instance, the striped shirt, thick blue jacket, black shoes, and other items shown here complement one another and form an appealing outfit, as demonstrated by the person wearing this outfit on the right. In fashion compatibility, we are interested in traditionally, several fashion recommendation systems have focused on retrieving items that are visually similar to each other. These items are similar in appearance and shape as depicted by the full body gowns. Further, the retrieved items also belong to the same category. Many applications such as in-shop item retrieval and shop the look make use of the concept of similarity. However, compatible item retrieval differs in many ways. While the retrieved items are often similar in appearance, they come in different shapes and belong to a different category as depicted with the fashion items on the left. This opens up a wide range of applications such as complementary item retrieval and fashion bundles. For example, if you purchase a blue handbag, then it makes sense to recommend a set of compatible items such as blue jacket along with it. However, unlike traditional item retrieval, this problem is very challenging since the model should be able to reason about the appearance and shape of the fashion items effectively. We now formalize the problem statement for fashion compatibility. Given an outfit consisting of a set of fashion item images as depicted in the figure, the goal is to train a deep neural network for fashion compatibility. Here, the model should place compatible items closer to each other than non-compatible items in an embedding space. During inference, the model is used to score the given outfit by computing average cosine similarity of all item pairs in the outfit. In order to learn such embedding, many studies have used metric learning approach, in which the anchor and its positive item are drawn from a compatible item, while the negative item is drawn from a pool of fashion items that belong to the same category as positive item. A CNN-based architecture is trained using the triplet laws to minimize the cosine distance of compatible items while maximizing the distance of non-compatible items with certain margin. Existing works aim to learn effective representations using deep neural networks. In one line of works, the authors train multiple representation spaces, one for each pair of category types. Therefore, it is impractical to deploy this method when the catalog consists of a large number of categories. In another group of work, the authors exploit structural nature of the problem and model fashion compatibility as a graph neural network. More recently, researchers have exploited attention mechanisms to aid in learning rich subspaces. All of these methods are fully supervised and demand access to large dataset. However, creating large labeled fashion outfits datasets is combinatorial and is therefore hard. A fashion corpus in typical e-commerce industry consists of millions of items. An expert carefully handpicks different combination of items to form an compatible outfit as depicted in the slides. So, this process is cumbersome and demands expertise. Therefore, in this work, we aim to reduce the dependency on a large label dataset by advancing a semi-supervised approach. In our semi-supervised setting, we are given a small labeled outfits dataset and a large pool of unlabeled fashion items. We use the metric learning approach on labeled fraction of dataset. Along with that, we aim to leverage large pool of unlabeled fashion items by exploiting the knowledge of fashion compatibility through data augmentation mechanisms and self-supervised learning. We first dig into the proposed data augmentation strategy by explaining the idea of pseudo-outfit generation. Consider an appealing labeled outfit that consists of multiple fashion items as shown. For a given image in the labeled outfit, if we replace it with a similar item, then we will obtain a compatible outfit. On the other hand, replacing it with a dissimilar item yields a non-compatible outfit. We make use of this idea to generate a large set of pseudo-outfits. We create them on the fly by randomly replacing one of the items with nearest neighbor in the training batch. For this reason, we use a sufficiently large training batch of unlabeled items subject to memory constraints. In this way, we construct pseudo-labeled outfits and impose an additional triplet loss. We now dig into the self-supervised consistency regularization. Here, we aim to instill the knowledge of shape and appearance of fashion items in a systematic way. We exploit the fact that compatible items often come with similar appearance but with different shapes. Accordingly, it's desirable for the model to learn shapeless features while simultaneously learning appearance-rich features. Therefore, it becomes important to capture the notion of appearance and comparatively give lower emphasis on shape information. To achieve this goal, we explicitly alter the shape and appearance of unlabeled fashion item by using techniques explored in self-supervised literature. We take an image from unlabeled corpus and apply shape transformation to obtain positive image instance, and apply appearance transformation to obtain negative image instance. More concretely, for shape transformation, we rotate the image in the range of 5 degrees, share the image at most 30 pixels, and we also scale the image by a maximum of 1.2 times and take center crop of the image. For appearance transformation, we employ grayscale conversion and color jittering techniques laid out in the listed papers. Since triplet loss encourages the appearance transformed image to ripple away from anchor embedding, the model learns appearance-rich embedding space. Putting it all together, we now explain our algorithm. We first sample a mini batch of labeled and unlabeled fashion items from the training dataset. We then create pseudo-outfits and transformed images as previously described. We then pass these images to the model and obtain embeddings. After that, we compute triplet loss for each instance in the labeled batch. We compute self-supervised loss for the shape and transform triplets, and similarly a margin triplet loss for the data augmentation. We compute the total loss as shown in the equation, where lambdas are the hyperparameters. We evaluate our method on two commonly used datasets called Polyvore and Polyvore disjoint datasets, which have been collected by users on Polyvore website. Since both datasets are relatively small in size, we curate a large-scale fashion outfits dataset from an online e-commerce site. We use the customer transaction history and association mining principles to create the dataset. Note that outfits in these datasets are more noisy than the Polyvore dataset. There are two subtasks in fashion compatibility. In a compatibility task, the goal is to classify if the items in an outfit are compatible or not. The second subtask is called fill in the blank task, where we are provided with images of items in an incomplete outfit, and the goal is to pick an item from the answered choice to complete the outfit. We report area under curve AUC metric and accuracy as performance for these tasks respectively. These are the results obtained by a method on Polyvore and Polyvore disjoint datasets. We segregate the methods into baseline methods, fully supervised methods, and semi-supervised methods. The second column indicates the fraction of dataset used by these methods. Further, we indicate that some of the fully supervised methods also use additional supervision in form of text embeddings and type information. Results indicate that our semi-supervised approach that uses only 5% of the labels is on par with fully supervised approaches and is outperforming the fully supervised baselines. We obtain similar results on fashion outfits dataset. Here, we compare our semi-supervised approach against a fully supervised type-aware method. Results indicate that our semi-supervised approach performs consistently better than some of the fully supervised approaches. Further, we conduct ablation studies for measuring the effectiveness of consistency regularizer and pseudo-labeling. Based on the results, it is evident that both these forms of regularization on unlabeled data have complementary benefits and improve overall performance significantly. We obtain insights into our method through systematic experimentation. First, we check the performance of our method as we increase the fraction of labeled outfits dataset. As we increase the percentage of labeled outfits to 100%, it is interesting to note that our approach is able to outperform many fully supervised approaches. Second, expanding fashion items in the unlabeled pool increases performance of the approach. As we increase the unlabeled batch size from 256 to 1024, the compatibility AUC increases from 0.84 to 0.86, as shown in the slide. In summary, we proposed a semi-supervised method for fashion compatibility. We have demonstrated that our data augmentation technique and self-supervised loss formulation can yield up to 5% improvements even when the labeled data is small. Thanks.
Thank you. Again, if you have questions, please ask them on the hub or come here to the microphone. I'm going to start with the same question I was going to ask you, that Magdalena Rignacchi now asks on the hub. Similarity, does that always equate compatibility? So sometimes replacing with visually dissimilar items will still result in a compatible or interesting outfit. So what's the reasoning around this visually similar equating compatible?
Actually, yeah, I think what I said is not exactly that. So similarity is not same as compatibility. So what I presented in the slides is that two items can be similar, but they need not be compatible. It's actually what you said. So I guess it is right. It is right that two dissimilar items can be compatible. I'm not sure if that answers your question.
Good enough, I think. Another question from the hub is it possible to make it unsupervised? It seems that the image might be a model with a whole set of outfit. I think maybe with an object detection model, the pseudo-labels can be generated in an unsupervised fashion.
Yeah, I think that's a great idea. It will be interesting to explore new directions, but that's definitely a very good idea.
Okay, we have a question from the audience in the house.
Hey, thanks for the interesting presentation. I have a question was kind of in line with the first question. So as you presented, it seems to be very tailored towards monochrome outfit sets, you know, all red, all blue, all black, that kind of stuff. And I was wondering if you could consider in your data augmentation not to just use a color jitter, but for instance, replacing items with another item that has a complementary color, leveraging color theory. Do you think that is a viable extension of your approach?
Absolutely. I guess I haven't mentioned all the details here, but we do use some of those techniques. I would encourage you to check the paper for that.
Thank you.
Another question from Team Virtual. In fashion, last year's items are no longer trendy and users are more likely to buy items that are new and have none or small numbers of purchases. Can you please comment on how you would approach these issues?
Yeah, one of the benefits of our method is that it's semi-supervised, meaning that even if we have a new group of fashion items that are not labeled, our approach naturally extends to this problem. Essentially, I think this is one of the problems in, I think that's a good question. So it is, by the nature of the approach, it's semi-supervised. So we don't expect that all the items that we have available are labeled. So I think that's a good use case for our approach.
Okay. Continuing on, do you see any differences in results in men's fashion versus women's fashion?
Well, yeah, I don't have an answer to that. Yeah.
Okay. There are more questions online, so please interact on the hub. Let's thank the speakers again. And we'll now move on to a bit of a different domain with